All right. I had some questions this week about how I'd like people to express numbers. And I wanted to talk a little bit about different notations that we have for real numbers and what my preferences are for this class. So, in my mind, there's sort of three major ways that we use to represent real numbers. We can use symbolic notation, or exact values, some people call that. We can calculate the decimal expansion of a real number, or this is a bit more specialized, we can use scientific notation. There's plenty of other variants of these things, but those are sort of the big three. And just as comparison, I want to focus on this particular number, and I've written it here as e squared plus the square root of 3 minus 1/2. So that might have already given away some of my opinions on this subject. So in symbolic notation, we are just writing the formula for the number. So this number is just e squared plus square root of 3 minus 1/2. So in principle, this is the exact value of this real number, or you could think of this as instructions for how to calculate this number or where to find it on the real number line. And in my mind, the main benefit of writing this out is that it makes Scratch work much easier to diagnose. So if I'm running a calculation and at some point I have to take the square of e, as I work through my notes, I can actually follow that number all the way through the calculations. Or if I have to go back and I have to ask myself, gosh, where did that square root come from? I can look a little bit back and actually make sure that the square root is the function that I'm trying to use there. It's a benefit for you as you're working on math papers, and it's also a benefit for me because it makes homework a lot easier to grade if I can see, what's exactly the step where maybe a mistake was made or something like that. Now, there are some downsides to this notation. Is this number positive or negative? I'd have to think about it a little bit. I know that e is bigger than 2. I think that 1/2 is less than that, so looks like I've got something positive here. Is this a very large number? Again, like I can think about these things, but it's not immediately obvious. So people might be more familiar with decimal expansions. And here I've written out the decimal expansion of e squared plus the square root of 3 minus 1/2 is all this stuff. 8.6211069064995525 and the rest. And that's a lot to take in. It's not really practical to keep all of those digits around, right? So this is an irrational number. This decimal expansion will continue infinitely without repeating. But for everyday usage, it's very common to just round to a certain number of decimal points. So this is no longer the exact value. The stuff I have on the left is not exactly equal to 8.62, but it's pretty close. Now, one of the benefits right away is that I can tell if this is a very large number or a very small number. Here I can say it's a little bit more than 8.5. I can also tell right away if it's a positive number or a negative number, since we'll just put a negative sign out on the front for negative numbers. So strictly speaking, this is giving me the exact value of the integer part, right? The integer that would be closest from below would be 8. And then how far from 8 is this real number? It's off by 0.62 and change. And this representation makes it much easier to perform basic calculations. Like if I had to square this number, I'd expect that to be something a little bit bigger than 64, since I know that 8 squared is 64, and the squaring function is an increasing function. Now, this benefit does start to break down when we look at very, very large numbers. And that is the reason why scientific notation exists. So you may not have seen this in a previous class, and that's fine. I just wanted to mention it since it's out there. In scientific notation, we'll say that only the first couple decimal places are significant. So here, I'm taking my same rounding as before. This number is about 8.62. And I'm also representing the magnitude of this number. So this notation makes a whole lot of sense when we're working with very, very large numbers. If I'm talking about something that's about 8.62 million, I don't really care about the hundreds place, and I don't really care about the tens place. That's not significant anymore when we're talking about that scale. Or likewise, if I was talking about something very, very small, if I was talking about a number that starts 10 places after the decimal point, I'd be representing that here in the exponent of 10. Or some calculators would write this as 8.62 E0. So that E there that you might have seen on a calculator is standing for multiply by 10 to this power. So this is very useful in context when you're working with very large numbers and very small numbers at the same time. And it lets you just sort of look at it and tell immediately which is the bigger thing. Again, if I had an 8-digit number and a 9-digit number right in front of me, I don't want to be counting all those by hand. I can just look at my representation, and the representation tells me, oh, 8 to the 9 is bigger than 8 to the 10. So what do I want for this class? Since we're using graphing calculators, we are relying on computers to do a lot of the arithmetic for us. And it's sort of the nature of mathematics that we're going to be working with a lot of numbers who have infinite decimal expansions. So certainly irrational numbers have infinite decimal expansions. They could be transcendental numbers like e and pi, or they could be algebraic numbers like square root of 2. And even most fractions have an infinite decimal expansion. Just the difference there is that it's going to repeat at some point. So 1 divided by 7 has infinitely many digits in its decimal expansion, even though it is a fraction. So calculators are familiar with certain irrational numbers, and they can say, it's like, okay, this calculator knows the decimal expansion for e. This calculator knows the decimal expansion for pi. But as your calculator is working, it doesn't have enough space to store every single digit. And so your calculator is making a choice to truncate somewhere and just round to the next digit up. And it does that all behind the scenes, which is very nice for day-to-day use. But the calculator is making that decision by itself. And every single time we ask the calculator to do something for us, it's going to make that rounding decision every single time we press the equals button, every time we ask it to evaluate some expression. So if you're doing a calculation and you're putting every single step in your calculator, then those small errors where the calculator is deciding where to round for you are going to add up over time. Now, it's not so bad when we're doing addition and subtraction. It gets a little bit worse when we're doing multiplication and division, right? So a small change when we're multiplying can actually have a very large effect on the outcome. And then it gets even worse when we're talking about exponentials and logarithms. Sort of the more complicated the function is, the more sensitive it is to rounding errors. So my advice for this is that while you're working on paper, on whatever scratch work you've got, please try to keep your writing in symbolic notation for as long as possible. So this would be things like keeping that square root of 2 as just radical 2 instead of writing 1.2 and stuff. Then, when you know the formula is done, you can put it into your calculator and you'll only need to use the calculator at one step. So that way the calculator is only doing the rounding once. And that's going to help us avoid rounding errors. And that way we'll get answers that look more or less the same. So you get the benefit of knowing what your calculations mean instead of having to track down, oh gosh, what is that 8.62? Where did that even come from? You can realize that, okay, well, this 1/2 had to come from somewhere earlier in the calculation. This square root had to come from somewhere earlier in the calculation. I personally find that very helpful when I'm doing scratch work of my own. And as a teacher, it also helps me understand where you're coming from when you do a problem. Once you do give it to the calculator, my preference is that we use just regular decimal expansion, so integer part decimals, and that we round to 2 places. Other classes will have other standards for how many figures is significant. Are we more concerned about the magnitudes of these numbers rather than the full expansion of those integer part and the decimal part? And that's very well and good. Those are very specialized ways of dealing with numbers. For this class, I'm most interested in teaching techniques of calculus. So the way that we handle numbers is not particularly important for that, right? I don't actually know what use case we're going to be working towards, but we need to settle on something. So what I ask is please 2 decimal places. Now, I may also ask for a problem where I say, please make this calculation and give me an exact formula for such and such number. And the answer to a problem like that might be, the answer is pi divided by 8, or the answer is the square root of 147, or the answer is cosine of 1.5, whatever that is. And it's not that I'm doing that to be obtuse. I want to make sure that people are understanding the problems that I'm assigning. And this is one of the ways that I have that lets me know that you're using the correct formulas and applying them to the correct parts of the problem. So if I get an answer back, it says 3.42, and the answer is 6.78, I don't know exactly what went wrong. But if I can see the square roots in there, or if I can see the exponentials or the logarithms, that's much more helpful to me as a teacher to be able to diagnose that and give some advice. Okay, I hope that that helps clarify some things. For the most part, decimal expansion, round to 2 places. And then every now and then I might be a stickler and ask for a nice formula instead. And that goes for fractions too. Fractions being one of the formulas we can use. All right, I'll see you later.